We have already discussed about performing inference and producing estimates on a Bayesian framework, and now we're going to discuss ways to summarize and present our results. The most important thing is to take into account the familiarity of our audience with Bayesian statistics and data analysis. So if you're speaking to an audience that's not very familiar, you might want to take some more time expanding on ideas such as prior, posterior distributions, and so on. A very common way of representing the posterior and predictive distributions is through their density plots. We have already seen examples in previous lectures using single variables. However, now we're going to consider an example with multiple variables. So consider a vector x consisting of variables x1, x2, x3 that follows a multinomial normal distribution with vector mean mu and variance-covariance matrix sigma. So we can imagine that things can be a bit tricky when it comes to plotting the joint distribution of vector x, as we now work on 3 dimensions, and as dimension increase it becomes more and more difficult. So this is why we introduce the idea of marginal distributions. So if we take the joint distribution of x1, x2 and x3 and marginalize out variables x2 and x3, we get the marginal distribution of variable x1. We can also consider the joint distribution for different pairs of variables. For example, we can find the marginal joint distribution of variables x1 and x2 if we take the joint distribution and marginalize out variable x3. Doing that can give us the following matrix. We can notice that diagonal elements include the density for the single variables and are one-dimensional as we have marginalized out 2 variables, and off-diagonal elements are two-dimensional and represent the marginal joint distribution for different pairs of variables. As we saw earlier, the covariance for pair 1, 2 is 0.8, and the covariance for pair 1, 3 is minus 0.7. The different sign is reflected through the change of direction in the joint distribution. And also we saw that the covariance for pair 2 and 3, for pair of variables 2 and 3 are 0.2, which is very, very low. And this is reflected by having a more circular joint distribution. In the case of the multinomial normal distribution, we're quite lucky because the expression for the distribution is available in closed form. However, as you will see later, there will be many cases when that's not the case and you only have a sample from the distribution. You have already seen that you can rely on that sample and use kernel density estimate to obtain estimates for the density over the grid. If we do that, we obtain the following plot. We can notice that it is fairly similar, however, the surfaces are less smooth than the previous case, and this is because we haven't evaluated the density exactly, but we have obtained estimates for it. Now we can consider a different case where we're not asked to provide any information about the uncertainty, and we're asked to only provide a single value about our variable theta. Here we consider an example of a beta distribution with parameters alpha is equal to 7 and beta is equal to 3. In that case, again, we are quite lucky and the distribution is available in closed form. We have already seen that for a beta distribution, we can evaluate the mean, which is our first point estimate, by finding alpha divided by alpha plus beta, in which case gives us 0.7. However, when that's not the case, we can obtain the posterior mean estimate by obtaining a sample from our distribution and using the mean function in R to evaluate the posterior mean estimate. We can see that the estimate is very close to the actual value of the mean, however, is not exactly 0.7 as it is only an estimate. A different point estimate that can be considered is the maximum posteriori estimate. This is defined by taking the value of theta with the highest density. Again, in our case, it can be evaluated numerically, as we have the expression in closed form. However, in cases where only a sample is available, we can use the following lines of code in R. What we do is we evaluate the density of a sample, and then we find the point with the maximum density. We can see in the plot, the purple line depicts the mean value, and then the green line depicts the maximum posteriori point estimate. The two-point estimates can be very useful for different types of problems. For example, if you're working on a decision problem, you are more likely to use a posterior mean because you want an average of the most possible values for theta. However, if you, for example, work on an optimization problem where you want the optimal value, you are more likely to choose the maximum posteriori estimate. Using posterior point estimates means that we disregard any information we have about uncertainty. Another way to summarize our results is through posterior intervals. Posterior intervals provide information about uncertainty and can be easily combined with point estimates. Here we consider an example of a mixture of beta distributions, and we consider two types of posterior intervals. The first is the central posterior interval. So first we need to decide on a significance level, which, say for example, we choose 5%. So how the central posterior interval is calculated is that we want to disregard half of the significance level, which means 2.5% from the lower tail and 2.5% from the highest tail. This can be easily done in R using the following lines of code. So first we sample from the mixture of betas, and having obtained a sample like that, we use the quantile function to obtain the interval. This can be slightly misleading because, for example, the value of 0.5 for theta is included in that interval when we can observe that it has very low density, very close to 0. Therefore, we consider another type of posterior interval known as the highest posterior density region. The highest posterior density region includes the values of theta that have density that constitutes the 95% of the highest densities. The problem that we can usually stumble upon is that it's very tricky to evaluate numerically, as it requires evaluation of integral equations. In our case, we use the package in R that is given by the following code. You usually need to install a separate package for it. You evaluate the density of the sample that you have obtained from the mixture of betas, and then use the function HDI, in which you enable the option allow split, which gives you the two discontinuous intervals that you can see. These are depicted with the green line.